Hi, welcome back to my class in Integral Calculus or Calculus 2. Last time we started using some of the integration rules, and for today's lesson we will have more examples in using some of these integration rules. And we started out last time with the integral of x to the n with respect to x. It is equal to x to the n plus 1 over n plus 1. And the exponent n is not equal to negative 1 plus the constant of integration c. Next, we have the integral of the exponential function e to the x with respect to x. In this integration rule, the exponent of e, the irrational number e, is a single variable x with an exponent 1 and numerical coefficient of 1. If the exponent of the base e is not a single variable, we have to make use of a technique of integration like substitution. But the integral of e to the x with respect to x is itself e to the x plus a constant of integration c. Next, we have the integral of dx over x, or the integral of 1 over x with respect to x. And it is equal to natural logarithm of the absolute value of x plus c, a constant of integration. We have to write x in absolute value notation to make sure that x is positive, because the natural logarithm of a negative number is not defined. Next, we have the integral of sine x with respect to x. The integral of sine x is negative cosine x plus a constant of integration c. In this integration rule, the angle x is a single variable with exponent 1 and numerical coefficient 1. If the angle is an angle other than x, then we have to make use of a substitution technique to express the angle of sine function as a single variable with an exponent 1 and numerical coefficient 1. Again, the integral of sine x with respect to x is equal to negative of cosine x plus c, a constant of integration. Next, we have the integral of cosine x, where the angle x again is a single variable with exponent 1 and numerical coefficient 1. The integral of cosine x with respect to x is equal to sine of x plus a constant of integration c. And the integral of tangent x with respect to x is equal to negative of natural logarithm of the absolute value of cosine x plus c. And it is also equal to the natural logarithm of the absolute value of secant x plus c. Later on, we will show that the integral of tangent x with respect to x is really equal to negative of ln of the absolute value of cosine x plus c, and it is also equal to ln of the absolute value of secant x plus c. In our examples today, we will make use of one technique of integration known as substitution. We have actually used substitution in some of the examples we had last time in the last lesson, but we specifically use algebraic substitution to transform the integrals to integrals that can be integrated using one or more of the integration techniques. Now we will have examples in using these integration rules. Example, consider the following problem. Evaluate number 1, the integral of cube of sine 2x dx. In this problem, we will make use of one of the Pythagorean identities for the square of sine x. If you are given an integral of sine to the power to an odd power or to an odd exponent, you you write it as the product of sine x and sine to an even exponent. Hence, we rewrite the cube of sine 2x as the integral of sine 2x multiplied by the square of sine 2x with respect to x. Sine 2x multiplied by sine squared 2x is the same as sine cube 2x. We have just rewritten sine cube 2x as the product of sine 2x and sine squared 2x in order for us to find the integral of this integrand. And you make use of this technique whenever the exponent of sine is an odd exponent or odd number, such as 3. Now, it is in sine squared 2x that we make use of the Pythagorean identity that says the square of sine plus the square of cosine is equal to 1. But instead of x, we will use 2x. In terms of 2x, this Pythagorean identity says the square of sine 2x plus the square of cosine 2x is equal to 1. And from this equation, we solve for the square of sine 2x by transposing cosine squared 2x to the right-hand side. Hence, we get the square of sine 2x. At the right, we have 1. And we transpose cosine squared 2x to the other side. And we take its opposite sign. It becomes negative cosine squared 2x. And in this, we now replace sine squared 2x with 1 minus cosine squared 2x. Now, the given integral, the integral of the cube of sine 2x with respect to x is now equal to the integral of sine 2x multiplied by sine squared 2x, which is equal to 1. Since this has more than 2 terms, we write it in open close parentheses, 1 minus cosine squared 2x. We integrate with respect to x. And we distribute sine 2x, multiply each of these terms by sine 2x. That's by applying the multiplication property, the property of multiplication. This is now equal to the integral of sine 2x multiplied by 1 is sine 2x. This is positive times negative is negative. Sine 2x multiplied by cosine squared 2x. We integrate with respect to x. Now we apply another property, another integration rule for the integral of a difference that says the integral of a difference is equal to the difference of the integrals. The integral of the difference of two functions is equal to the difference of the integrals of the two functions. By that integration rule, the integral of this difference of these two functions is equal to the integral of sine 2x with respect to x minus the integral of sine 2x cosine squared 2x with respect to x. For the first integral, we make use of a substitution. For us to be able to make use of this integration rule, the sine of x. Here, the variable is a single variable x with exponent 1 and coefficient of 1. But here, we have the sine of 2x. The angle is not a single variable x but has a coefficient of 2. Hence, we will make use of substitution by letting u equals to x. Let u equals to x, and we differentiate both sides. Derivative of u is 1 multiplied by du or du. Derivative of 2x is 2 multiplied by dx. In the given integrals, integral of sine 2x dx, we replace 2x with u, and we have to replace, we also have to change the variable of integration to u by solving for dx from this equation by dividing both sides by 2 or multiplying both sides by 1/2. We multiply the left hand side by 1/2. We get 1/2 du equals multiply 2 dx by 1/2, and if you multiply this by 1/2, you get 1/2 multiplied by 2 is 2 over 2 or 1 multiplied by dx is dx. In the first integral, we will replace 2x with u, and we replace dx with 1/2 du. And then we apply this integration rule. The integral of sine is negative cosine plus the constant of integration. For the second integral, the integral of sine 2x cosine squared 2x with respect to x, we will also make use of a substitution by letting u equals cosine 2x. Cosine squared 2x is the same as cosine 2x to the power 2. Let me rewrite that as this cosine squared 2x is the same as cosine 2x squared. The squared of cosine 2x is the same as cosine squared 2x, or cosine squared 2x is the same as cosine 2x to the power 2. And we let cosine 2x be equal to u. Let u, for the second integral, we let u equals cosine 2x. And we differentiate both sides. Derivative of u with respect to u is 1. Multiplied by du is du. And derivative of cosine is negative sine 2x. And by chain rule, because the angle here is not simply x, it has a coefficient of 2, we apply the chain rule. Derivative of cosine is negative sine 2x times the derivative of 2x is 2. Multiplied by differential of x or dx. In the second integral, we have sine 2x and dx. And we can solve that we can solve for sine 2x dx from this equation by multiplying both sides by negative 1/2. We multiply the left side by negative 1/2. Negative 1/2 multiplied by du. And we multiply the right hand side by negative 1/2. Negative 1/2 multiplied by sine 2x. We write first 2 multiplied by sine 2x is 2. Multiplied by sine 2x dx. We have negative we multiply both sides by negative 1/2. The right hand side is multiplied by negative 1/2 multiplied by negative 2 times sine 2x there, 2 times sine 2x with respect to x. From the right hand side, negative times negative is positive and 2 will cancel out. Hence, the right hand side simplifies to sine 2x dx. Sine 2x dx is now equal to negative 1/2 du. For the second integral, we replace cosine 2x with u, and we replace sine 2x dx with negative 1/2 du. After the substitution for the first integral, we apply the integration rule for sine. For the second integral, after the substitution, we apply the power rule for integration. Now do the substitution. The integral of sine cubed 2x with respect to x is equal to integral of sine dx we replace with u, sine u, and dx we replace with 1/2 du, multiplied by 1/2 du, minus the integral. This is cosine squared 2x, as we said, is equal to the square of cosine 2x. But we let cosine 2x be equal to u. Hence, cosine squared 2x is equal to u to the power 2. Or u squared. Multiplied by sine 2x dx is equal to negative 1/2 du. Multiplied by negative 1/2 du. To each term, we apply the integration rule for the integral of a constant times a function. That says the integral of a constant times a function is equal to the constant multiplied by the integral of the function. Here the constant is 1/2. So the integral of sine u 1/2 du is equal to the constant 1/2 times the integral of sine u with respect to u. The second term, we have negative times negative is positive. And the constant is also 1/2. By the integration rule for a constant times the function, this integral is equal to the constant 1/2 multiplied by the integral of u squared with respect to u. For sine u du, we apply the integration rule for integral of sine. And the integral of sine, we said earlier, is equal to negative cosine u. Our variable of integration now is u, where u is 2x for the first term. So the first term is equal to 1/2 times the integral of sine u with respect to u is negative cosine u plus 1/2. For the integral of u squared, we apply the power rule for integration, where the exponent n in the power rule is 2. Hence, the integral of u squared is u to the power 2 plus 1 is 3. And divide by 3. This is actually 1/2 multiplied by u cubed divide by 3 plus the constant of integration c. In the first term, our u is 2x. In the second term, our u is cosine 2x. And we replace u here with 2x and u here with cosine 2x to write the answer in terms of the original variable x. We have 1/2 times negative is negative 1/2. Cosine u is 2x plus 1/2 multiplied by 1/3 is 1/6. U is cosine 2x. Cosine 2x is u. Cosine 2x to the power 3 plus c. Or you may factor 1/2 from the first term and the second term. Or you may leave them as is, as in negative 1/2 cosine 2x plus 1/6. The cube of cosine 2x is the same as cosine cube 2x plus c. This is the integral of the cube of sine 2x dx. The integral of sine cube 2x dx is equal to negative 1/2 cosine 2x plus 1/6 cosine cube 2x plus c. For our example 2, consider the following integral. Number 2, integral of cosine 3x multiplied by e to the power sine 3x dx. Again, we will make use of a substitution to transform the given integral into an integral that can be integrated using one or more of the integration rules. I will let u be equal to sine 3x. Let u equals sine 3x. And then we differentiate both sides. If you let u be equal to cosine 3x and you are unable to simplify the given integral so that it could be integrated by using one or more of the integration rules, then you try to make use of u equals sine 3x. Differentiating both sides, derivative of u with respect to u is 1. Multiplied by du is du. And derivative of sine is cosine. Cosine of 3x because the angle is not a single variable x with exponent of 1 and coefficient of 1, but it is 3x. We apply the chain rule. Derivative of sine 3x equals derivative of sine cosine 3x multiplied by derivative of 3x is 3 multiplied by dx. Or we write, now by inspection of the given integral, we have cosine 3x multiplied by dx. And we can solve for cosine, the product cosine 3x and dx from this equation by dividing both sides by 3. You divide the right side by 3, the left side by 3. Or multiply both sides by 1/3. And 3 here will cancel. You get cosine 3x dx. Cosine 3x multiplied by dx is now equal to du over 3. We now substitute 3x with u, and cosine 3x multiplied by dx we replace by du over 3. Hence, the given integral is now equal to the integral of the integral of e to the power sine 3x. Sine 3x is u. Cosine 3x multiplied by dx is du over 3. Multiplied by du over 3. And we apply the integration rule for the integral of a constant. Constant here is 1/3 multiplied by the function. By that integration rule, the integral of a constant times the function is equal to the constant 1/3. Multiplied by the integral of the function e to the u with respect to u. And we said earlier that the integral of the exponential function e raised to some variable is equal to that same function e raised to that variable. Hence, the integral of e to the u is e to the u. We have 1/3 times the integral of e to the u is e to the u plus a constant of integration c, or 1/3 multiplied by e. We now write the final answer in terms of the original variable x by replacing u with sine 3x plus a constant of integration c. The integral of cosine 3x e to the power sine 3x with respect to x is 1/3 multiplied by e to the power sine 3x plus the constant of integration c. Consider another example. For our example 3, we have the integral of ln of x dx over x square root of ln of x plus 1. Again, we will make use of a substitution to transform this integral into an integral that can be integrated using one or more of the integration rules. And we usually let an expression to be equal to u, or another variable, whose derivative is also found in the given integral. If you let u be equal to ln of x, and you are unable to simplify and transform the given integral into one that can be integrated using one or more of the integration rules, then you try to use another substitution. I will let u be equal to ln x plus 1. We let u be equal to ln x plus 1. And we differentiate both sides. Derivative of u is 1. Multiply by du. 1 times du is du. Is equal to derivative of ln of x is 1 over x. Multiply by dx. We have dx over x. And derivative of 1 is 0. Dx over x plus 0 is dx over x. Now, we will now replace ln of x plus 1 with u. In the given integrand, we have dx over x, and we replace that with du. But we have to get rid of ln of x, otherwise we would have two variables in the integrand, x and u. From this equation, u equals ln x plus 1. We can solve for ln x by transposing positive 1 to the left-hand side. Hence, ln of x is equal to u, and we transpose positive 1 to the other side, we get minus 1. In the given integral, we replace ln of x with u minus 1. We replace dx over x with du. And the radicand ln x plus 1 we replace with u. Hence, this integral is now equal to the integral of ln of x, u minus 1, multiplied by dx over x is du, over the square root of ln of x plus 1 is equal to u, square root of u. And this can be integrated already by using power rule. But first we have to simplify. We write square root of u as u raised to 1/2. We have the integral of u minus 1 with respect to u. Divide by u raised to 1/2. And we bring u raised to 1/2 to the numerator by taking the opposite sign of 1/2. We bring u raised to 1/2 to the numerator, and we get the integral of u raised to 1/2. That's by property of exponent, multiplied by u minus 1. Multiply by u minus 1 with respect to u. We distribute, we apply the property of multiplication. By distributive property of multiplication, we multiply u and 1, negative 1 by u raised to negative 1/2. And we apply property of exponent for the product of u, negative 1/2, multiplied by u. The exponent of u here is 1. And when we multiply, we add the exponents, negative 1/2 plus 1. We get integral of u. This is negative 1/2 plus 1 here, the exponent of u. Negative 1/2 plus 1 is 1/2. Negative 1 times u to the negative 1 half is negative u to the negative 1 half. To integrate with respect to u. And we apply the integration rule for the integral of the difference of two functions that says the integral of the difference of two functions is equal to the difference of the integrals of the two functions. Hence, the integral of this difference is equal to the integral of u raised to 1 half with respect to u. Integral of u raised to 1 half with respect to u minus the integral of u raised to negative 1 half with respect to u. Now we apply the product rule for integration to integrate each term. In the power rule for integration, the exponent n is 1 half. And we add 1 to 1 half. 1 half plus 1 is 3 halves. This is equal to u to the power 3 halves. Divide by n plus 1 is 3 halves. Divide by 3 halves. Minus, for the second term, the exponent n in the power rule for integration is negative 1 half. And we add 1 to negative 1 half. Negative 1 half plus 1 is 1 half. U raised to 1 half. Divide by n plus 1, 1 half. Plus the constant of integration c. And we simplify each term and we replace u with ln x plus 1. The numerator divided by 3 halves is the same as the numerator multiplied by the reciprocal of 3 halves is 2/3. 2/3 multiplied by u ln x plus 1. To the power 3 halves. Minus, to simplify this fraction, numerator divided by 1 half is equal to the numerator times the reciprocal of 1 half, which is 2. We get minus 2 multiplied by u. U is ln x plus 1. To the power 1 half plus c. And we simplify further each term by writing each term in terms of radical expression. The integral now of ln x dx over x times the root of ln x plus 1 is equal to 2/3 by property of radical. Ln x plus 1 raised to 3 halves is the same as the root of ln x plus 1 raised to 3. 2/3 multiplied by the root of ln x plus 1 to the power 3 minus 2. Again, by property of radical, ln x plus 1 raised to 1 half is the same as the square root of ln x plus 1. Square root of ln x plus 1 plus the constant of integration c. The root of ln x plus 1 raised to 3 can be written as, we have 2/3 We write this as ln x plus 1 square multiplied by ln x plus 1. The exponent of ln x plus 1 here is 1. And by property of exponent, we have the common base ln x plus 1. The exponent of this product will be 2 plus 1 is 3. We have just written ln x plus 1 raised to 3 as ln x plus 1 squared multiplied by ln x plus 1, so that we can extract the root of ln x plus 1 squared. The second term will be the same as is, minus 2 multiplied by the root of ln x plus 1 plus c. Now, by property of radical, the root of this product is equal to the roots of ln x plus 1 squared multiplied by the root of ln x plus 1. But the square root of ln x plus 1 squared is ln x plus 1. Hence, the first term is equal to 2/3 multiplied by the square root of ln x plus 1 squared is ln x plus 1. And multiplied by the root of ln x plus 1. Minus 2 multiplied by the root of ln x plus 1. This may already be your answer, but if you want to write your answer in factored form, the two terms have common factor of 2 and square root of ln of x plus 1. We'll factor those factors from the two terms. We have 2, common factor is 2, and square root of ln x plus 1. Multiply by 1/3. The first term, 2/3 ln x plus 1 times square root of ln x plus 1. Divide by 2 times square root of ln x plus 1. 2 will cancel out. And square root of ln x plus 1 over square root of ln x plus 1 is 1. So for the first term, we get 1/3 times ln x plus 1. And the second term, 2 square root of ln x plus 1 divided by 2 times ln x plus 1 is 1. Minus 1 plus the constant of integration, c. Hence, the integral of ln x dx over x times the root of ln x plus 1 in factored form is 2 times square root of ln x plus 1 multiplied by quantity 1/3 times ln x plus 1 minus 1 plus c. This can still be simplified by multiplying 1/3 by 1, and you add 1/3 minus 1. But this may be this is already acceptable as the answer for the integral of ln x dx over x times the root of ln x plus 1. Before we apply the integration rule for the integral of tangent x equal to negative ln of the absolute value of cosine x plus c, or the integral of tangent x dx equals ln of the absolute value of secant x plus c, we show that the integral of tangent x dx is really equal to negative ln of the absolute value of cosine x plus c, and also equal to natural logarithm of the absolute value of secant x plus c. Tangent x using one of the ratio identities is equal to the ratio of sine x and cosine x. By one of the ratio identities, tangent x is equal to the ratio of sine x to cosine x. We integrate sine x over cosine x with respect to x, and we make use of substitution by letting cosine x be equal to u. We let u equals cosine x, and we differentiate both sides. Derivative of u is 1, multiplied by du. 1 times du is du. And derivative of cosine x is negative sine x dx. In the numerator, we have sine x dx. From this equation, we solve for sine x multiplied by dx by multiplying both sides by negative 1. If we multiply the right hand side, negative sine x dx by negative 1, we would get positive sine x dx equals, we also multiply the left hand side by negative 1. Negative 1 multiplied by du is negative du. Now in this integral, we replace cosine x with u, and the product sine x multiplied by dx we replace by negative du. This integral now is equal to integral of tangent x dx is equal to the integral sine x times dx is negative du over cosine x is u equals, since negative 1 is a constant, we apply the integration rule for the integral of a constant times the function, that says the integral of a constant times the function is equal to the constant, here it's negative 1, times the integral of the function 1 over u with respect to u. And the integral of du over u is ln u minus, this now equal to negative, times the integral of du over u is ln u plus a constant of integration. We write u in absolute value because we are not sure if u is positive, and u has to be positive for the natural logarithm of u to exist. And to write the answer in the original variable x, we replace u with cosine x. This now equal to negative ln of the absolute value of cosine x plus c. Hence, we have shown that the integral of tangent x with respect to x is negative ln of the absolute value of cosine x plus c. To show that the integral of tangent x with respect to x is also equal to ln of the absolute value of secant x, we add 0. We have 0 minus ln of cosine x plus c. But 0 is equal to ln of 1 minus ln of cosine x plus c. And to the difference of ln of 1 minus ln of cosine x, we apply one of the properties of natural logarithm that says the ln of a over b is equal to ln of a minus ln of b, where a is 1 and b is cosine x. Thus, the integral of tangent of x dx is equal to ln of 1 over cosine x by this property of natural logarithm. Ln of 1 over cosine x plus c. And one of the reciprocal trigonometric identities says that 1 over cosine x, this is the reciprocal of cosine, is equal to secant x. Therefore, the integral of tangent x dx is equal to ln of the absolute value 1 over cosine x is secant x plus c. Thus, we have shown that the integral of tangent x with respect to x is either equal to negative ln of the absolute value of cosine x plus c, or the integral of tangent x dx is equal to ln of the absolute value of secant x plus c. For our next example, consider the following problem. We have evaluate the integral of sine squared x dx over 1 minus cosine x. In this example, we will make use of the integration rule for one of the trigonometric functions. But first, we have to transform this given integral into an integral that can be integrated using one of these integration rules. And to do that, it's either you make use of a substitution or we make use of a trigonometric identity from your course in plane trigonometry. In this example, we will use a trigonometric identity, particularly one of the Pythagorean identities that says the square of sine x plus the square of cosine x is equal to 1. In the given integral, we have sine squared x in the integrand. Hence, we solve for sine squared x from this Pythagorean identity by transposing cosine squared x to the right-hand side. We have sine squared x is equal to 1. We transpose positive, we take the opposite sign, we get negative, minus cosine squared x. Hence, the given integral is now equal to the integral of sine squared x is 1 minus cosine squared x. Divide by 1 over cosine x. And integrate with respect to x. Now, to simplify further, we make use of factoring, special product, a factoring method to factor out the numerator. In the numerator, we have the difference of two squares. We have 1 is the square of 1, and we have the square of cosine. And one of the factoring methods is for the difference of two squares. According to this factoring rule, the difference of two squares, such as the difference of a squared and b squared, can be factored as the product of a sum and difference of a and b. Hence, a squared minus b squared is equal to a plus b multiplied by a minus b. And we apply this factoring rule for the difference of two squares to factor out 1 minus cosine squared x. Hence, this integral now is equal to the integral of 1 minus cosine squared x. We apply this factoring rule for the difference of two squares, where a is 1 and b is cosine x. And the factors of 1 minus cosine squared x are 1 plus cosine x and 1 minus cosine x, all over 1 minus cosine x. And we integrate with respect to x. And you can see now that 1 minus cosine x in the numerator and in the denominator will cancel out. And we simply have the integral of 1 plus cosine x with respect to x. And we apply the integration rule for the integral of a sum of two functions that says the integral of a sum of two functions is equal to the sum of the integrals of the functions. Hence, the integral of 1 plus cosine x with respect to x is equal to the integral of 1 multiplied by dx, or integral of dx, plus the integral of cosine x multiplied by dx. And the integral of dx is x. The integral of cosine x from our integration rule is sine x, plus the constant of integration c. Thus, the integral of sine squared x dx over 1 minus cosine x is equal to x plus sine x plus c. Now consider our next example. We have the integral of sine x minus times quantity 1 minus secant x dx. Again, we have to transform this integral into one that can be evaluated using one of these integration rules. And we make use again of a trigonometric identity from your plane trigonometry. We distribute sine x by distributive property of multiplication. We multiply 1 and negative secant x by sine x. Hence, the given integral is equal to the integral of sine x multiplied by 1 sine x minus sine x multiplied by secant x and we integrate with respect to x. From our plane trigonometry, secant x is equal to the reciprocal of cosine x. The reciprocal of cosine x, this is one of the reciprocal identities from plane trigonometry. The reciprocal of cosine x, or 1 over cosine x, is equal to secant x. We replace secant x with 1 over cosine x. We have the integral of sine x minus sine x multiplied by secant x is equal to 1 over cosine x and we integrate with respect to x. We multiply sine x multiplied by 1 is sine x over cosine x. This is now equal to the integral of sine x minus sine x multiplied by 1 is sine x over cosine x. Integrate with respect to x. But again, from plane trigonometry, this is one of the ratio identities. The ratio of sine x to cosine x is equal to tangent x, or tangent x by ratio identity is equal to the ratio of sine x to cosine x. Thus, we replace sine x over cosine x with tangent x. This is now equal to the integral of sine x minus tangent x with respect to x. And now we apply the integration rule for the integral of difference of two functions, that says the integral of difference of two functions is equal to the difference of the integrals of the two functions. Thus, the integral of the difference of sine and tangent is equal to the integral of sine x with respect to x minus the integral of tangent x with respect to x. Now, the first integral of sine with respect to x is now readily integrable using one of the integration rules, as well as the integral of tangent x with respect to x, it is now integrable. And we know that the integral of sine x with respect to x is negative of cosine x. Minus the integral of tangent x. And in our example earlier, we have shown that the integral of tangent x is either equal to negative of ln of the absolute value of cosine x, or the integral of tangent x with respect to x is equal to ln of the absolute value of secant x. I will use the integral of tangent x with respect to x equals negative ln of the absolute value of cosine x. We have minus integral of tangent x is negative of ln of the absolute value of cosine x plus the constant of integration c. Again, for the integral of tangent x with respect to x, I use negative ln of the absolute value of cosine x. And we simplify by multiplying negative and negative. We have negative cosine x. Negative by negative is positive. Positive ln of the absolute value of cosine x plus c. Thus, we have evaluated the integral of sine x times quantity 1 minus secant x with respect to x is equal to negative cosine x plus ln of the absolute value of cosine x plus c, the constant of integration. For your practice, please try the following exercises. Evaluate the given integrals. Exercises, evaluate. Number 1, we have the integral of 3x e to the power x squared dx. In number 1, you will use algebraic substitution to transform this integral into one that can be integrated by using one of the integration rules. In number 2, we have the integral of 2x dx over x squared plus 2. In number 2, you will also use algebraic substitution to transform this given integral to one that can be integrated by one of the integration rules. Number 3, we have the integral of cosine cube 5x dx. In number 3, you have to use a Pythagorean identity. You write cosine cube 5x as cosine 5x multiplied by cosine squared 5x. Then you make use of trigonometric identity for cosine squared 5x. In number 4, we have the integral of ln x minus 1 over all over x times ln x. We integrate with respect to x. In number 4, you have to use a substitution to transform this integral into one that can be integrated using one of the integration rules. Number 5, we have the integral of sine x dx over the root of 1 minus cosine x. In number 5, you have to use a substitution. Use an expression whose derivative is also in the given integrand. In number 6, we have the integral of x tangent x minus 1 all over x, and you integrate with respect to x. To transform this into an integral that can be integrated using one of the integration rules, you divide each term of the numerator by x, and you proceed from there. If you have any questions about the lesson today, you ask your questions in the comments below. Thank you for joining in my class today, and don't forget to subscribe in my YouTube channel, Art Kalisan. Thank you.